All right, so we've got W being x1 plus I, y1, and Z being x2 plus I, y2. Now, a common property that we are going to keep using is, so remember this and maybe, prove it to yourself many times. Make sure you're okay with that. So the conjugate of Z squared is Z times Z bar. So remember, if I'll just quickly do it for you to remind you, if I let Z be A plus IB, for example, we know the length of it is the square root of A squared plus B squared. So if I square that, I'm just going to get A squared plus B squared. If instead I do Z times Z bar, the conjugate, again, we're going to get A squared, the IAB and the minus IAB cancel each other out, and then I'm getting negative I squared B squared. I squared is -1, so negative B squared, so plus B squared. So they're going to be the same. So that is the property that we kind of keep using over and over again. So make sure you maybe memorize that one. Okay, so that's what we're going to use here. So also remember, a little trick is, this is what they've asked us to prove. Show that the distance of WZ between the points W and Z is conjugate Z minus W. So that's what we're asked to show. But that can be a bit tricky. So instead, what we can end up showing is the square of each side is equal to each other, and then get there. So that's a bit of a trick. We can do that instead, and then therefore mod Z minus W equals mod WZ. Okay, so let's work on that. So let's start with mod Z minus W squared. Okay, now by this property, we can rewrite that as Z minus W and Z minus W conjugate. Okay, just by that property. Okay, so remembering Z is this and W is this. Let's take the reals. We're going to have x2 minus x1 for the real part, and if we subtract the imaginary part, we're going to have y2 minus y1, and then we're multiplying that by, okay, so now we want the conjugate. Well, we just got that, so we know it's the same as that, but the conjugate. So we're going to have x2 minus x1 minus I, y2 minus y1. Oops. Okay, so that's what we're going to have. Now we already know, because of what we just did, what we're going to get. We are going to get, and you can do it, well, let's do it again, but it's just a bit harder to see because we've got so many things. You are going to get that x2 minus x1 all squared, but the I terms, let's do it in a gift colour, so I times x's and the y brackets, and the other one, this one, minus I times the x, y, they're going to cancel each other out. So the only other term we're going to get is, oops, and I did the wrong thing there, is negative bracket times negative, sorry, I bracket times negative I bracket with the y's in it. So you're going to get negative I squared, which is positive y2 minus y1 squared. So we already know we're going to get that. And that is just WZ all squared. So the length from W to Z all squared. That's what that is. So if we square root both sides, because they're all positive, both sides are positive, so we can say Z minus W is equal to, mod Z minus W is equal to a length of WZ. Okay. And then, so it's just asking you to have a little look at, show that the angle of the line WZ makes with the positive real axis is the argument Z minus W. Well, if we just make this length the same as this length, I mean, you can see it geometrically anyway, but length WZ would equal length OP if we just shift that line over. So when we're saying what angle does it make here with the horizontal, it's the same as that angle. So angle, let's say ZWV is going to be equal to angle POX. So we're finding that theta. We already know the angle is arg Z minus the argument of Z minus W. because this is the same. So it's position vectors go from 0, but you know, if we're thinking of vectors, that vector can move over here, no problem. So just asking you to have a little look at that and see that theta is the argument of z minus w, because this is the vector as z minus w. Okay.